mute us off. It's always, hi Sergio, we miss you. I hope you can visit sometime. Okay, so buy the book. So for this part of the course, you can download it online. But so this is a book on controlled queuing networks. But Chapter 9 was written to be self-contained. So it does mention CRW, meaning controlled random walk queuing networks, a couple times. It doesn't matter. I mean, it starts off with a countable state space Markov chain and gives you everything, it's using the notation that we've been using in the course so far. So it's, but this is really complete, and I'm not going to be so complete. So I gave you this firm foundation of Markov chains. You have enough material to read this. I'm not going to read it to you. So I'm going to give you a lot of theorems without proof. And a lot of the proofs are very similar to proofs in the non-controlled case. I'll give you examples as we go along. But anyway, Chapter 9 of this, I'll put this in the reading assignments, and I'll give warnings about what how much depth you should go into. But so now it's all controlled Markov chains. Yeah.
What is when you entered last class, you briefly spoke about the discounted cost last time when you did value iteration and stuff. That's a linear set of equations, right?
Yeah.
Couldn't you directly solve for it if you be?
Oh no, absolutely. All right. So the question is, so last time we were talking about value iteration, and then. And I didn't really have time, but I guess I threw it out there. For the discounted case, what are we trying to do? We're trying to solve C plus beta P, beta P H equals H, right?
Yeah.
And it's a matrix inverse.
Right, and I think...
that's what I was saying last time. H is just equal to, so put this to the other side, I minus beta P inverse C, and that's it. Yeah. So in MATLAB, that's what I was saying. Value iteration is kind of stupid. If you're trying to solve that equation, successive approximation is probably the dumbest approach you could use. Yet it's the most common approach that's used.
I guess you do introduce nonlinearity when you go for the optimal case, though, right?
When we get to optimal control, then it's a nonlinear fixed point equation, and successive approximation is a little more natural. It's still damn slow. But that was the main reason. So my motivation for introducing value iteration last time was to teach you about coupling, and that same coupling argument's used in proving value iteration is convergent in Markovian in controlled settings as well. So you can now go back and read the proof in the controlled setting. It's the same thing. It's more technical, of course, because it's a control. Right?
I guess total cost cases won't work, though, right? Because the inverse doesn't.
No, it does. Right? So in the average cost, remember we have that H is equal to I minus P tilde inverse C. That's that's one representation. In a finite state space setting, that's always going to work.
Of course, everything fine.
All right. Okay, so you can imagine now we have So unfortunately, people in operations research came up with Markov decision process, and they took over the language. I think it's ridiculous. Markov decision process. It's a controlled Markov chain. It's just it's a control problem. So we have what do we have? We have so what? It's a controlled transition matrix. Or kernel you know, if we're in a general state space. There's a cost function, and there's a criterion, which I'll explain. So it's a triple, if you like. You know, there's dynamics, a cost function, and by criterion I mean like discounted cost, average cost, the total cost of some other sort, all sorts of things like that. All right, and we are going to be in trouble with these pens. Black's a bit better. Okay, and so PU, the same notation as before. So before I had, well, you know, I've got PU now, x to y, is the probability that xt plus 1 equals y given xt equals x, and now u2 equals u. And I'm not in love with sticking the u down there, but, you know, it makes it easy to write down equations that I'd like to write down. So everybody, what does this mean? You can guess. If that's my definition of transition probability, you know, how would you have me define this? It's a conditional expectation of what? Of h, just like before. Yeah. That's it. Okay. So there's the notation. So nothing changes like that. And so let's go look at what I mean by these criteria. All right. So number one is discounted cost. You know, so we introduce a discount factor beta, and just like we were talking over there, now we're going to have an H star beta of x, which is equal to the minimum of all u. Put a little x there. All right, and so, I mean, again, I guess I left out some notation, didn't I? So x is still in some state space x as before, but u is living in somewhere as well. You know, so uk is in some set. I need a fancy symbol for that, like something like that. and unfortunately, in the computer science community, they call this the action space. It's the input space or action space. It's just that the control community let their guard down for about a decade. It was always called the input space, and the CS community called it an action space. So UK is just some set. Well, you know, typically assume it's finite, but not. We really won't. I mean, when I describe algorithms and write these things down, I'll assume that the state space is countable and the input is finite or something. But when we come to examples, that won't be true anymore, and you'll just have to, you know, just accept that these ideas generalize. No. Okay, so there it is. So I'm minimizing over all sequences in this action space, and of course I have other conditions on U, right? So the main thing is it can't be clairvoyant. You know, I'm making decisions now to maximize my income. If I knew the future, I'd make a lot of money. So UK is some function of the past. So put it like this: UK is in some sigma field fk for all k, and the sigma algebra generated by the x's is contained in fk. Now, why do I make a big deal about that? Is that I want to allow for randomized policies. So I want to be able to, you know, time k, look at the history of state variables, and also flip a coin and make my decision based on that. So I'm allowing randomized decisions. So, you know, this looks very abstract, but we'll make it, you know, basically, again, notation. Yeah. That's a typical setup, you know. I mean, in every application you ever look at, you're going to find your state dynamics look like that. You can have a nonlinear state space system where the new state is a function of the old state in the input and some ID noise. I think they call it a disturbance. And then I use phi here because phi stands for feedback. So the input uk is some function of xk and some noise, wkID. Now, I could always extend the state space. I could always say phi k equals xk wk. And that's Markovian. So I can always extend the state space. So I could always, without loss of generality, I could make these equal just by state space augmentation. All right. So that's typical. We'll see why that's typical as we go on. All right? Okay, so back to 1. So I'm minimizing here over all sequences U that are, you know, functions of my measurements up till time k. And then, you know, we've already done this in a way, but let's do it again. So just peel off the first term there. And so I've got my initial cost here, and then my cost to go, and let's just really expand this out. So again, that giant U, if you want me to, I'll write 0 to infinity. You know, look at minimizing over sequences, over stochastic processes. Now, I've got my U naught here, and this is something that only depends on the future, so I can go and take conditional expectations and so forth. And then I take the so I look at all possible places I can be at one step in the future, all right? And then I take the expectation given y, and I use my Markov property. I have to shift everything by 1. Oh shit. That's confusing, isn't it? Nah, it's dangerous. Sorry. Let's be more careful here. Fuck. U0 is going to be a variable, right? I'm minimizing over sequences. The first U0 is just going to be, it's a function. forget any randomization. This could be a function of x when I minimize. It's going to be just a deterministic quantity. So this is, you could just think of that as a joke. Damn, I didn't realize I wasn't. I didn't realize that I needed notes for this. I don't know how to write this down in an elegant way.
Are you trying to like express it in terms of the PUs?
Well, I'm trying to say it. No, you know what I'm getting at. You all know I'm going to write down a DP equation I wrote down in lecture 1. But it's just that because I've written down a sequence of U's here, oh, I know what I have to do. I have to take the sum inside. There's a lack of clarity here that's bothering me. Oh, yeah. Forget all that crap. Let's see. Let's stare at this for a while. I hate it when I get screwed up like this. But anyway, I've got this random variable here, which is the thing I didn't realize I need to bring up my shift operators to make this clear. You know, I want to write this as theta 1 times the original thing we're interested in. You know, basically. I sort of didn't realize, I forgot that you really need to think in terms of shift operators and stuff. That I'm looking at the expectation x of some random variable h, and that h is this discounted sum. And then as soon as I do this, it's like I think about, I'm starting from time 1 and then looking forward to the future. And basically this whole sum is just a shift of that h, except the annoying extra beta. You know, this whole thing is like beta times theta 1 of h. And I didn't realize that how unclear this would be. I just thought I could do this off the top of my head. So I'm gonna come back to you with a clear exposition next time. But because of this and the Markov property, this is equal to, I can basically take the minimum here and say, obviously we know 8 star is defined to be the minimum of this. So at least I could replace the expectation given x1 here by its minimum. I'm just going to write it down again. I don't know if this is helping or not, but that's why this damn strong Markov property is so nice. The notation is so elegant because I'm shifting this random variable, which of course depends on my inputs and x's. I'm leaving it out. And I know that the conditional expectation of theta 1h given f1 is I just plug in the expectation xh. Crazy. Sergio, I'm sorry, it's not usually like this. So it's much simpler than this if your professor comes prepared. But maybe it's good that I slow down. I mean, you know, this is a fact, this is a fact, was a stupid thing to write down because you need your notation. That's a fact. You know, H is a random variable that depends on the sequence of random variables I choose, but it doesn't make any difference. And then there's still going to be this property for these in this controlled setting. We're still going to be able to say this. We're still going to have this generalization of the Markov property. And then you look at this and you say, well, that thing is all, you know, for any input sequence I put in, the smallest this could be is that, right? That thing is upper bounded by H star at x1, and I can achieve that, you know, by applying the policy that was good for that x1 starting point. So there's a very long way of saying that H star beta of x is the minimum over just little old u of C of xu plus beta pu H star at x. And again, big space there, because you hit H star by pu and then you evaluate it at x. Now that's the conditional expectation. There's a beta there. Phew, all right. All right, so again, I'm going to send you a simpler derivation of this, either in notes or in lecture. Okay, so the second one is I'm going to give you sort of a version of the shortest path problem. So I take a subset of my state space and I look at the total cost up until I get to that target state. And sometimes you put next to a terminal cost at the end. You know, that's a possibility. I'm leaving it out just for simplicity, okay? You know, just imagine so I've got a little car here, and it's going around and wants to get to the top of the hill. And basically, when it gets to the top of the hill, it can hit the brakes and stop. So basically, there's energy costs and things like that. Costs for getting too close to a cliff, you know, and yeah. So this is one of the AI gym. One of the AI gym examples that maybe we'll play with, and maybe we'll you'll solve one of these. I don't know. How to get to the top of the hill with minimum energy of something. Now, this you can go through the same thing if you're careful. And since that turned into such a mess, I think I'll give you, I'll forget the shift operators and sort of write it down. But what's going to be different? Here, is just an infinite sum. And here, you can see the difference. Oh, and tau s is the same thing. Remember, tau s equals the minimum of k greater equal to 1, such that xk is an s. All right. So that's what's different. I mean, basically, when I go through and I look at the initial cost plus the cost to go, that's what this is called, by the way. In these DP equations, that's always called, the one-stage cost and the cost to go. That's the way to always think about this. There's a big difference. Basically, in one step, I could be an S and the whole thing's over. And so you have to look at those two possibilities. And I put in the tau s minus 1 just so that things disappear if that happens. All right? So let's see if we can play with this. All right, so basically, tau s is always going to equal to 1, so we always get the first term again. And then the remainder, it's basically, I'm saying that I'm not in S1. I'm not in S, I'm sorry. And rather than having to write out that cumbersome thing here, I'll just use the same notation, just put a little x there. All right, now, I'm not going to do it. And you can imagine why. I could say this is a shift of something, and then I'd have to explain to you that the shift is really the same thing. Because if I'm not in x1 at time s, then the shifted version of tau s is itself. It's really just the next time to hit s. Because I'm basically thinking of x1 as my new initial condition, and looking at the first time greater equal to where I am, to the time where I am now, to reaching s, and that doesn't change. So this turns out to be exactly what you'd think, exactly what comes out over here. It's equal to the minimum over just little old u of c of xu plus this whole thing I'll get rid of that. I need my u now. So I've got what I'm writing down here. And then this ends up being just H star. So again, there's sort of discounting, but now the discounting is through an indicator function instead of a beta. It's basically, I've got something here which is less than or equal to 1. And so this is sort of a discounting. So it suggests that you could easily solve this equation through some sort of iterative scheme. All right? That this causes a contraction, just like the beta causes a contraction over there. All right? Anyway, there it is. That's the Bellman equation, the DP equation. I guess I didn't use that language. That you always hear about. All right. So there it is. And that, again, I realize we'll come back to try to make this clearer to you, because I can see this requires more clarity. But that's not how you'd write this down, right? The way you'd write this down is you'd use our notation. So this whole monster could be boiled down to what? Except that x1 is y, y is not an s. So y is an s complement. And if you wanted to go full operator notation, you'd write 8 star, well, forget it, let's not do that. You'd replace this, put an indicator function in there. Oh, let's do it. It's equal to the minimum over u, c of xu, plus pu hitting is complement 8 star, and then evaluating at x. All right, just practice that notation. So I take my 8 star, I multiply it by an indicator function, which is 1 if I'm an s complement and 0 otherwise. Hit that by this transition matrix, and then evaluate at x. That's the same thing. All right? No? You don't like it? What? You like this better? Yeah. Okay, all right, cool. So that's the DP equation for the shortest path problem. Now, here's number 3, and this is fun. So, average cost. Because it's a miracle you can do anything. So I'm going to So it turns out the theory is much prettier if you make everything random. And I'm going to call that, say, eta of u. How's that? Because I've been using eta for the steady state mean. Sorry. So you look at that, and you look at that, and you see how on earth could I make a connection? No way, right? So a bit of history is the 1960s. So basically, you can solve this minimization problem by solving a linear program, all right? And then I'm not sure who did it, but a little later, somebody came up with a dual. The dual is the average cost optimality equation, which I'll explain to you. And, oh, that's right, we have a name for this too. So for any input u, input sequence u, just call this whole thing eta of u, could be infinite, could be whatever. But it's a limit supremum, so limit supremums always exist. I mean, they could be infinite. But the minimum over all u under extremely general conditions, exists. It's unique. It doesn't depend on the initial condition. I'll give you conditions, extremely general conditions. And so you get this wonderful equation, which is just exactly, this is like the discounted cost dp equation without control we talked about before. Poisson's equation is what comes up. I'll just put it over here. All right. So one clumsy way to derive this, is to go and look at this and say to yourself, hey, I'll bet when I let beta go to 1, then this will somehow converge to something, And those H tilde tricks that I gave you in the homework, that's what allows you to justify it. You throw away, you write down H beta star as the tilde part plus a constant. Remember the homework? The whole reason I did that homework was to make this clear. So you can take H beta star and write it as a bounded term plus a constant. And the constant, you just can take it outside basically. It doesn't depend on anything. And then the tilde part is bounded in beta. You let beta go to 1, gives you that. And beta there. Oh, did I put a beta in there? Just because I was thinking ahead of this conversation. So again, you write this down as its tilde part and a constant, and the tilde part converges to this H star you see here.